Okay, let's move from Thevenin to maximum power transfer. The maximum power is transferred from a source to a load when the load resistance is equal to the internal source resistance. The maximum power transfer theorem assumes the source voltage and resistance are fixed. So these principles might seem pretty straightforward, but we want to make sure that when we are analyzing or designing a circuit and we Thevenize it, we have our V Thevenin and R Thevenin that is going to be connected to the load. That R Thevenin better be the same as the R load. That way, the R load gets the maximum power transfer. So that is the basic rule. So this is another criteria that we can use not only for loading effect, but also if we want to find the maximum power transfer. And you might think, oh, maybe this might be a smaller, and this is a smaller, I'm gonna get more power here, and that is not the case. The mathematics works in the way that it just only happens when these two are the same. So that's something to keep in mind. So what is the power delivered to the matching load? So we have 10, we have 5. We find the power to the load by using the source, since we have 50% of the voltage here and 50% of the voltage that makes it a 5 divided by the resistance, and that gives 0.5 watts. So that's how that works. Pretty straightforward. Okay. Superposition. Superposition theorem is a way to determine current and voltages in a linear circuit that has multiple sources by taking one source at a time and algebraically summing the results. So superposition, it is a linearity characteristic, so we can use it only in linear systems. Okay, a linear system, it's only a resistive circuit. So a circuit that only has resistance as part of its electronic components, we can use superposition. Once we add capacitors, inductors, we cannot apply superposition unless when we are working at a specific linear operating points for those components. Otherwise, we cannot use superposition. So it's very important to keep that superposition is only valid when we have a linear circuit. Otherwise, it's violated and we cannot use it. But in essence, what superposition is, we have multiple sources as part of the circuit, and those sources are not in series. Therefore, we cannot simplify it like we did in our midterm. If these two sources were in series, then we can just add them up or subtract them, and then we have an equivalent source. But they are not. You see, they come here and then they are connected here, but there is something else connected here. So we don't know. So we don't know how they split, how to add them up. So we cannot solve this circuit by just adding these two voltages to a resultant or equivalent voltage. So we have to use superposition, or we have to use different techniques to solve a circuit like this. So we are going to solve it using superposition because that's what we are learning. But basically, superposition it says that when we have different voltage sources and current sources, or a mix, we can have voltage sources or we can have current sources. And the way it works is we analyze the circuit source by source. We leave one source in the circuit and we remove the rest of the circuit sources. We replace it by its internal resistance equivalent. Like if it is a voltage source, we short. If it is a current source, we open. But when we analyze the circuit, it has to be one voltage source at a time. We have to keep track of the direction of the quantity that we are solving for, in this case I2. We have to keep track of the polarity, or in case of current, the direction. So once we add the map, we take into consideration the direction, because it's not always the same direction. So they don't always just add up. Sometimes they subtract, sometimes they add up, sometimes it's a mix of the two. So it's important to do that. So let's solve this. I think I worked it out. Yes, I did. So we have a circuit and we are solving for I2. So I'm going to find or solve for I2 when B source 1 is left on. The other one is removed. So the other one gets removed by a short. So this is my equivalent circuit. Once I have it like this, you can apply your understanding of circuit analysis. So I said this one and that one are in parallel. So the parallel combination of that I call R equivalent ones. Then this is my equivalent circuit. Now I can find my R total by just summing R1 and R equivalent 1. So my R total is R1 plus R equivalent 1, which is 6100 ohms. Now I can find my I total or my I source by dividing the voltage by the current. That gives me 1.97 milliamps. Now I'm going to do a current divider at node A right here. I'm going to say I'm interested in I2, so I'm just going to solve for I2 using the special 2 resistor current divider formula that I have, that is just the opposite, which is R3 divided by the sum of the two multiplied by the total current entering. So that gives me a 983.61 microamps, and that is coming down due to S1. Now I'm going to find I2 due to BS2. So for here, I'm going to put back the BS2 source, which is 18 volts, and I'm going to remove the other source right here. And in this case, R1 and R2 are in parallel, so that is my equivalent to R1 in parallel with R2. I get 1.93 kilo ohms. Then this is my equivalent circuit. My R total is just going to be R equivalent 2 plus R3. So R total is R equivalent 3 plus R equivalent 2 to be 8.73 kilo ohms. Likewise, using Ohm's law, I solve for I total. B total is over R total. That gives me 2.06 milliamps. I use current divider at node A. So I'm interested in I2 again. So I use again the formula for a 2-branch resistor, which is opposite R1 over R1 plus R2 times the total current coming into it. So I get 585.47 microamps. So this is also going down. So in this case, my I2 resultant is going to just add up. So I2 due to source 1 plus I2 due to source 2. So if I add them up, I get 1.57 milliamps. And I guess that makes sense because why does this make sense? Because the two voltages are on the same polarity, so yes, they should add up. So yes, they add up and the result is 157. See what they get here? They didn't give us an answer, so I'm pretty sure that's right. Okay, so let's move on. Oh yeah, they gave us an answer right here. They read that 157 milliamps. Is that what we read? Yes, 157 milliamps. So they said set up a table of pertinent information and solve for each quantity. So source 1, we get 6.10, 197 milliamps. I2 is 98 milliamps. Due to source 2, 0.8, they add up. So yes, they add up because they both have the same direction. So that's good over there. Troubleshooting the effectiveness. Troubleshooting must think logically about circuit operation analysis. Understand normal circuit operations and find out the symptoms of the failure. Planning. Decide on a logical setup step to find the fault. Measurements. Following the steps in the plan, make measurements to isolate the problem. Modify the plan as necessary. So yes, you have to understand how the circuit is supposed to operate for you to start creating a plan on how to fix it, and that comes with practice. Troubleshooting it says the output of the voltage divider is 6 volts. So we have a voltage divider here. Describe how you would use analysis and planning in finding the fault. So you have 6 volts here. Why? Why do you have 6 volts when this resistor is higher than that resistor? So this resistor should be, in the previous example, should be about 8 volts. So what happens here? So they says, from earlier calculation, V3 should be equal to 8.10 volts. A low voltage is most likely caused by a low source voltage or incorrect resistor. Possibly R1 and R2 are reversed. Okay, so they say, let's stop, don't worry about R3 yet. Let's just analyze here. If the circuit is new, incorrect components are possible. Decide on a logical setup to locate the fault. You can decide to 1. Check the source voltage. Yes, make sure you are actually inputting 15 volts. Disconnect the load and check the output voltage. Yes, disconnect that and make sure that you are actually getting a high voltage here. At least the 8.10 volts. Check the load resistance. If R3 is correct, check the other resistance. Yes. So first start with the basics. Check the voltage. The voltage is not 15. Then make sure it is. If not, remove that. Make sure you get a higher voltage here. Then make sure the resistors are in the right order. The key terms: loading effect. Loading, the effect on a circuit where an element that draws current from the circuit is connected across the output terminal. Low current, the output current supplied to the load. The bleeding current, the current left after the load current is subtracted from the total current into the circuit. The Wheatstone bridge, which is a very important derivation in resistance, can be measured using an unbalanced state. Thevenin, maximum power transfer, and superposition. So you can read those on your own. So that concludes chapter 6.